In a world fixated on lithium-ion technology and hydrogen storage, a revolutionary approach to energy storage is quietly developing in laboratories across the globe. Quantum batteries represent not just an evolution, but a complete paradigm shift in how we might store and distribute energy in the future. Today, we'll explore this fascinating frontier of science that harnesses the peculiar properties of quantum mechanics to potentially transform our relationship with energy forever. Unlike conventional batteries that rely on chemical reactions to store energy, quantum batteries leverage the strange and powerful principles of quantum mechanics. These cutting-edge devices store energy in quantum systems such as atoms, molecules, or specially engineered quantum materials. At the heart of this technology lies quantum entanglement, the phenomenon Albert Einstein famously described as spooky action at a distance. This fundamental principle allows particles to be connected in ways that defy classical physics, creating possibilities that were once thought impossible in energy storage. In March 2023, researchers at the University of Adelaide and their international collaborators achieved a remarkable breakthrough. They demonstrated that quantum entanglement can enable multiple batteries to charge simultaneously in a phenomenon called quantum superabsorption. This represents a fundamental departure from classical physics, where charging multiple devices requires dividing the available power among them. In quantum systems, however, the collective behavior of entangled particles can actually enhance energy absorption rates. This counterintuitive property could allow quantum batteries to charge exponentially faster than their conventional counterparts, potentially solving one of the most significant limitations in current energy storage technology. The field of quantum batteries is advancing at a remarkable pace. Just last month, scientists at the Center for Theoretical Physics of Complex Systems in South Korea developed a quantum battery prototype using superconducting qubits. Their groundbreaking design achieved an impressive 90% charging efficiency while maintaining quantum coherence long enough to make practical applications feasible for the first time. Meanwhile, researchers at the University of Michigan created a different approach to quantum batteries using defects in diamonds called nitrogen vacancy centers. This innovative method allowed them to store quantum states at room temperature for several milliseconds, an eternity in quantum computing timeframes and a crucial step toward practical applications. Currently, most quantum batteries exist only as theoretical models or small laboratory prototypes with capacities measured in microwatt-hours, far from what would be needed for everyday applications. However, the field is experiencing explosive growth, with over 200 research papers published in 2023 alone, compared to just 12 in 2018. The theoretical foundations for quantum batteries were established over a decade ago, but recent experimental progress has accelerated dramatically due to advances in quantum computing hardware. Many of the same technologies that enable quantum computers, such as ion traps, superconducting circuits, and quantum dots, are now being repurposed for energy storage applications, creating a virtuous cycle of innovation between quantum computing and quantum energy research. The quest for practical quantum batteries is being pursued through multiple avenues. Research teams at Harvard, Oxford, and the Max Planck Institute have demonstrated promising results using different quantum systems, including molecular magnets and photosynthetic complexes inspired by natural energy harvesting processes. These diverse approaches suggest that quantum batteries may eventually come in many forms, each optimized for specific applications. This variety of research paths increases the likelihood of success and indicates that quantum batteries could become a versatile technology applicable across numerous fields and industries. The most immediate applications for quantum batteries may not be powering electric vehicles or homes, but rather quantum computing itself. Quantum computers require precisely controlled energy delivery to maintain their delicate quantum states, and quantum batteries could provide an elegant solution to this challenge. This symbiotic relationship between quantum computing and quantum batteries creates a fascinating feedback loop. Quantum computers help design better quantum batteries, which in turn enable more powerful quantum computers. This technological synergy could accelerate development in both fields, leading to breakthroughs that might otherwise take decades to achieve. Beyond computing, quantum batteries could revolutionize medical implants. Their theoretical ability to charge extremely quickly and maintain charge with minimal degradation makes them ideal for devices like pacemakers or neural implants, potentially eliminating the need for replacement surgeries. Perhaps most intriguingly, quantum batteries might enable entirely new forms of wireless power transfer. Researchers at MIT are exploring how quantum entanglement could allow energy to be transferred between quantum batteries at different locations without conventional transmission methods. This could potentially enable new forms of distributed energy networks, where power is shared across quantum entangled devices, regardless of physical distance, a capability that sounds like science fiction, but is grounded in the principles of quantum mechanics. The environmental implications of quantum batteries are equally significant. These devices could theoretically achieve near-perfect energy conversion efficiency, dramatically reducing waste heat and energy loss during charging and discharging cycles. In a world increasingly concerned with energy conservation, this property alone could drive adoption once the technology matures. Satellite and space applications represent another frontier where quantum batteries could excel. The extreme conditions of space, particularly the cold, isolated environment, actually provide advantages for some quantum systems that operate best in these conditions. Quantum batteries could provide lightweight, ultra-efficient power sources for the next generation of space exploration vehicles and satellites, extending mission durations and capabilities beyond what's currently possible with conventional power systems. Despite the exciting progress, quantum batteries face significant hurdles before commercialization. The primary challenge remains maintaining quantum coherence, the delicate quantum states that make these batteries possible for practical durations in real-world environments. Quantum systems are notoriously sensitive to external interference, including temperature fluctuations, electromagnetic fields, and mechanical vibrations. Materials science represents another bottleneck. Researchers are still searching for ideal quantum materials that can reliably store and release energy while maintaining their quantum properties at practical temperatures. Current prototypes typically require extreme cold, often near absolute zero, which limits practical applications. Overcoming these fundamental challenges requires interdisciplinary collaboration between quantum physicists, material scientists, and engineers. Scaling remains perhaps the most formidable challenge in quantum battery development. While quantum effects can be demonstrated in laboratory settings with small numbers of particles, maintaining these effects at scales necessary for practical energy storage requires solving complex engineering problems. Researchers are exploring hierarchical approaches where multiple small quantum batteries are networked together, preserving quantum advantages while achieving useful energy capacities. This approach may allow quantum batteries to overcome the scaling limitations that have hampered other quantum technologies. According to Dr. Jens Eisert of the Free University of Berlin, who heads a major quantum battery research initiative, the timeline for the first commercial quantum batteries is likely 7 to 10 years away, with initial applications in specialized fields like quantum computing infrastructure and aerospace. Mass market applications might take 15 to 20 years, though he notes that quantum technologies have a habit of surprising us with both unexpected challenges and breakthroughs. As quantum battery research progresses from theoretical physics to applied engineering, we're witnessing the birth of an entirely new energy paradigm. The implications extend beyond mere improvements in existing technology. Quantum batteries represent a fundamentally different approach to energy storage that could enable capabilities previously considered impossible. Funding for quantum battery research has increased dramatically in recent years, with significant investments from both government agencies and private companies. The European Union's Quantum Flagship Program has allocated €30 million specifically for quantum energy research, while in the United States, the Department of Energy recently established a dedicated quantum energy initiative with $25 million in initial funding. This influx of resources is accelerating progress and attracting top talent to the field, creating a virtuous cycle of discovery and development. The convergence of quantum information science, materials engineering, and energy technology is creating a fertile ground for innovation in quantum batteries. This interdisciplinary approach brings together experts from fields that traditionally had little overlap, resulting in novel solutions and accelerated progress. While quantum batteries may not replace conventional batteries in all applications, they will likely enable new technologies and capabilities that we can only begin to imagine today. The unique properties of quantum systems, particularly entanglement, superposition, and coherence, offer pathways to energy solutions that simply cannot be achieved with classical systems, no matter how advanced. This fundamental advantage drives continued investment and research despite the significant challenges that remain. As we stand at the threshold of this quantum energy revolution, one thing is clear: the future of energy storage will be shaped not just by chemistry and materials science, but by the strange and powerful principles of quantum mechanics. The silent revolution in quantum batteries may soon make its presence known in ways that transform our relationship with energy. From enabling new computing paradigms to revolutionizing medical devices, from creating more efficient energy systems to powering the next generation of space exploration, quantum batteries represent one of the most promising frontiers in energy technology. While challenges remain significant, the accelerating pace of breakthroughs suggests that quantum batteries will move from laboratory curiosities to practical technologies faster than many expect, potentially becoming a cornerstone of our future energy infrastructure. Quantum batteries represent far more than just another step in energy storage evolution. They embody a fundamental reimagining of how we harness, store, and distribute energy using the deepest principles of physics. From the quantum entanglement that enables superabsorption to the diverse approaches being pursued in laboratories worldwide, we're witnessing the early stages of a technology that could redefine our energy landscape. While significant challenges remain in maintaining quantum coherence, developing suitable materials, and scaling these systems to practical sizes, the extraordinary pace of recent breakthroughs suggests these obstacles will be overcome. As quantum batteries move from theoretical concepts to experimental prototypes and eventually to commercial applications, they promise capabilities that conventional technologies simply cannot match: near-perfect efficiency, ultra-fast charging, novel wireless energy transfer, and perfect integration with quantum computing systems. The convergence of quantum physics, material science, and energy engineering is creating a new technological frontier with implications that extend far beyond batteries themselves, potentially transforming everything from medical implants to space exploration. The quantum energy revolution may be silent now, but its impact on our future will likely be profound. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.